Hey guys, what's going on? All right, we are going to make this extremely simple, extremely quick, and extremely straightforward if we possibly can because it deserves exactly that. We're talking about current law right now. We just went through Kirchhoff's voltage law if you watched the last video, and I thought that was pretty straightforward. But if you thought that was easy, you're going to think this is a breeze. And we're going to get through this in record speed. Here we go. Okay, we're going to talk about current law in series because that's where we're going to start. We're going to talk about the concept of junctions really quickly. We're going to give the definition, and then we're going to give an example circuit. Nah, I'm throwing that all up. We're going to talk about the definition first, and then we're going to talk about how dumb that something this simple has a definition this long. So, the definition, the actual definition, the algebraic sum of all currents entering and leaving a junction must equal to zero. And that could be signified with the mathematical expression sigma I, or sigma current in, is equal to sigma current out. What a load of crap. Let's jump in. Indulge me for a moment, because I am going to draw a simple wire, and I'm going to draw it in the proper color. All right, let's get this out of here. And let's say we have a current going through this wire. We're going to call this 1 amp of current running through this wire. And let's just put a point on this wire right here. We're going to call this bad boy point A. A, right here. And we got current running through the wire, and we take a measurement before point A, and we say, lo and behold, 1 amp of current, because that's what we have set up in our fictitious scenario. Let's measure the other side of point A, which is just a random point in the wire. And sure enough, 1 amp on the other side. Well, that's convenient because that's the way electricity works. Let's throw it up a little bit more. Let's put another wire in here. And we're going to add a resistor. Ooh, right? Resistor. And we're going to throw 1 amp going through a simple circuit with 1 resistor in there. Resistance doesn't matter. Let's just roll with it. And if we took a measurement on the other side of the resistor, starting over here and then looking at it this side, lo and behold, 1 amp of current. And this is not voodoo, this is what we expect. Current going into a wire is the same at the end of the wire if we're in a series circuit and we're not looking at a parallel circuit. That makes perfect sense. So that point that we put in there, we can pretend like that is a junction. It really is a useless junction because it's just a single point that has a wire going into it on one side and a wire coming out on the other side. The resistor could also be seen as sort of a junction. It's just a place within the circuit where we can evaluate the ongoings of the circuit. So let's do this. I'm going to mix this up a little bit more. And we're going to make a junction that looks now like this. I'm going to mark this junction. We're going to still call this point A because we're not feeling particularly creative tonight. And we're going to say that there is 5 amps of current that's going into this junction. And we'll say that we have some component, some measure of resistance further down line that's drawing 3 amps of current going down the junction. Well, what Kirchhoff's current law dictates is by knowing the current going in to a junction and knowing at least one of the variables going out, we can surmise what the duration or the rest of the current is that's going on through the system. And we can do this with that fancy mathematical equation, sigma I in is equal to sigma I out, which is basically saying, you ready for the real definition? What goes in must come out, and vice versa. What came out must have gone in. So if we have 5 amps going into a junction, 3 amps going off of one of the shunts, what do we have coming on the other side of the junction? Must be 2 amps. And the rationale is simple, right? 5 is equal to 3 plus 2. We can think of it as we have shed 3 amps somewhere down line, and 2 amps are going on further. Let's take a look at a parallel circuit with a little more detail, and we'll see how this works out. Alright, so I've created a very simple parallel circuit with resistances in there that are completely inconsequential, so they don't matter. I've labeled 3 vertical branches that the current is going to go through, and we know that we're messing around with a parallel circuit. The current can go through independently, and it's not going to be a universal value like in a series circuit. So these branches that we have here are A, B, and C, and we can expect that the current is going to go through each one of these branches in its path back to the negative terminal of the battery. And the resistances don't matter, because what I'm really concerned with is how much amperage or how much current is being shed through each of the branches as it goes through, so that we can make sure that this law is holding true. So let's take a quick look. Let's look at the current. We've got 9 amps coming out of the battery, and it's going to do the full gamut all around the battery. But let's say that at this first junction right here, at the top of branch A, it's going to shed off, we'll say 4 amps. And I like using the term shedding amperage, because I feel like that's really accurate. Like, the current is being drawn down another branch, but if you want to look at the path of the electrons or the charge carriers around the circuit, the current is actually being shed as it's being split amongst the different paths that it can take. It's like a choose your own adventure for electricity. Now that's fun. So we have just shed 4 amps going down branch A. So using what we know, I'll give you a second to guesstimate how much current is going to continue on. Huzzah, you're brilliant. That's absolutely right. If we have 9 and we've shed 4 amps going down branch A, then we actually have 5 amps if we were to measure at this point. That is carrying on. So let's say we've got our 5 amps going, and then we're going to shed 3 amps, or we're going to have 3 amps being drawn down branch B. How much current is moving on beyond the circuit? What we want to know is how much current can we expect to find at this point between branches B and C of the top positive rail. And if you said 2 amps, you are 100% correct. So let's go back really quickly and see why we're getting these values. So we're starting with 9 amps, and we're going through until we hit our first junction. 4 amps is being shed off. 4 is going down branch A, which means we have 5 amps continuing on through the circuit. 4 plus 5 is equal to 9, and 9 removing 4 has 5 carrying on. In our next branch, branch B, we have 5 amps that are continuing through the circuit because 4 have been drawn down branch A. 5 amps take away 3 because it's being drawn or shed down the B branch. We now only have 2 amps carrying on. So what happens here? We're at the end of this parallel circuit, and we know that the charge carriers are on a mission to achieve balance. So just like we know about electrons and charge carriers, they're going to continue their path. They're going to continue to move around. But I want to ask you, how many amps do you think are actually at this point between the 2 nodes at the top and bottom of branch C? Take a second thinking about it. Hold it in your head. And if you answered 2 amps, you're absolutely correct. 2 amps is continuing around the circuit in its path to go achieve equilibrium amongst the bias and the battery. Coming back around the bend, we still have 2 amps here at the bottom. We've had 9, we shed off 4, then we brought it down to 5, shed off 3, we still have 2 amps, and then we're going all the way back around the loop. So now I have to ask you, coming back on this bottom rail just past junction B, How much amperage do you think is between this area right here? And before you answer, I want you to remember what goes into a terminal, what goes into a node must come out and vice versa. So let's take a look at this node so we can get a better understanding of what's going on. We actually have two sources of amperage that's coming in. We've got one source of 3 amps coming in, and then we have our 2 amps that are continuing from going around the circuit coming in. So we have two inputs, 3 plus 2 coming together. And we know that as our output must equal our input and vice versa, then that must mean that that current actually rejoins, it comes back to become whole. So that means at this period beyond the bottom junction right here between branches B and A, we're actually back to 5 amps. Think about that for a second. We're starting to achieve this equilibrium and getting back to being whole as the circuit is continuing, as the current is going through the circuit. And now we're coming up to another junction. Right here, at junction at the bottom of branch A, we have 4 amps coming in and 5 amps rushing in as well. So what's headed back into the negative side, the negative terminal of the battery? It's our 2 inputs together, and they have to equal the same as the output, or vice versa. The output has to equal the same as the 2 inputs. So that means we have 9 amps going back into the terminal. And here we have a wonderful consequence of this observation, Kirchhoff's current law. 9 amps is leaving the battery, and 9 amps is returning into the battery. We've achieved this equilibrium. You know, I've said it before that electronics are a masterful display of balance and equality, and here we're seeing it right now. The current that's leaving is equal to the current that comes back when you're observing Kirchhoff's current law. I hope you enjoyed this video. I will see you next time. I think we will be talking about divider circuits. Since we now know both of Kirchhoff's voltage and current laws, we can throw them together and have some more fun. I'll see you next time, guys. Thanks. Can we just have a moment to appreciate Gustav Kirchhoff's simple observational laws? Yeah, I think so. Are you not recording? I don't know what you're doing. I think we're recording. Fair enough. Because there's no button that says you're recording, which leads me to believe that you're not recording, even though I pressed the button to have you record. Doesn't matter. Let's do this.